Hi, this is Bert de Vries. This is the second part of the Bayesian machine learning lesson in the Bayesian machine learning and information processing class. In the first part of this class, of this lesson, we introduced the framework of Bayesian machine learning, and we saw that it's all just application of probability theory. You propose a model, and from there on, it's all probability theory. We're going to do this now. We took the example of a coin toss, and we're going to work this out now. So in this video, or in this part of the class, we're going to actually make some actual assignments to these probability distributions and see how that works out. So as we said in the previous lessons, we start here with a coin, and we throw that coin a couple of times, and we observe heads, tails, heads, heads, tail, tail, heads. And the question is, what's the probability that heads comes up next? And so you have to start now by making or proposing a model. The model that you're going to use for this prediction task. And so let's start. We're going to denote outcomes. We're going to encode outcomes by x of k, and x of k is either heads, h if head comes up, or tails if tails comes up. If you could have chosen 1 or 0, it doesn't matter. You have to encode the outcomes. Now you have to make a choice for your data generating distribution and for your prior. The simplest thing we can assume about a coin is, well, there's a probability for heads, and let's say that the probability for heads equals mu, and mu is a number between 0 and 1. Right? This assumption is called a Bernoulli distribution, and the distribution that results from multiplying all these, or a lot of these Bernoulli distributions, is the binomial distribution. So the probability distribution for the observed data set, where D here stands for the observations here, HT, HITT, H, given mu is the product of the individual probabilities for each coin toss. And if I assume that I get n, small n heads, and as a result also capital N minus n times tails, then this probability, the probability for the data, is mu to the power n times 1 minus mu, the probability of throwing tails, to the power n minus capital N minus small n, which is basically the number of times that you threw tails. So now the data generating distribution has been defined in terms of a parameter, a property of the coin, and basically of your observations. Your observations are small n and capital N minus n, the number of heads and the number of tails. Now you need to make an assumption about mu. You need to make a choice about mu. You can just choose it to be a value, a half, and then basically you are done with your model assumption. But you don't know, let's assume you don't know if this is a fair coin. The coin may be slightly bent, so this probability for heads may not be exactly half. So let's state this basically this knowledge or this belief by a probability distribution. And now you need to go to the literature on probability theory and find probability distributions on the domain between 0 and 1, because we need a probability distribution for mu, and mu is only, we know mu is going to be a number between 0 and 1. There are a number of probability distributions defined on the domain 0 to 1, and one of them is the beta distribution, and the beta distribution happens to be a really good one. So the beta distribution is defined as indicated here in this formula. So we say the prior probability, or the probability for mu, is a beta distribution over mu, and we give this beta distribution two parameters, alpha and beta, and this is basically the expression. So this is an expression in the parameters alpha, beta, and then mu to the power alpha minus 1, 1 minus mu to the power beta minus 1. The nice thing about this beta distribution is that basically all the terms in mu kind of look the same as the binomial distribution. And you can imagine that if we start multiplying the beta distribution times the binomial distribution, we get another distribution that's going to be either binomial or beta again. In this case, it turns out to be a beta distribution. And that's a really nice property because it means we can actually solve our equations analytically. So let's choose the beta distribution. And by choosing different values of alpha and beta, you can sort of instill the amount of knowledge that you have about mu. I'll give a few examples here. If you would choose alpha is 1 and beta, alpha and beta here. Here's in the figures, here's A and B. But if you would choose alpha and beta both equal to 1, you basically say that your prior distribution for mu is a uniform distribution. In other words, you're saying, I have no idea, I have no knowledge at all about this coin. There's as much chance for it to be a totally unfair coin that always lands on heads or always lands on tail, or a fair coin. Basically, you have no information about this coin. But you can choose other values for A and B. You can choose values 0.1 and 0.1, which basically says that either you think it's very much, it's going to land a lot on tails, or it's going to land a lot on heads, but there's a very low probability that it's a fair coin. And there are other choices for alpha and beta that makes you basically you have the flexibility to encode any kind of knowledge you have about this coin. Once you've done that, you have a prior distribution. You have to make a choice for alpha and beta. You have a prior distribution and you have a likelihood function. So in terms of your assumptions, your model specification, you're done. From now on, it's just sum and product rules and just computations. So let's absorb the data into the model. We do that through Bayes rule, as we've discussed before. So we're going to compute the posterior for mu. What do we know about mu, given also the data? There are basically two sources of information about mu. One is your prior. You have made an assumption about mu by your beta distribution, and you can put in there, by making choices for alpha and beta, any kind of assumptions about this coin. But we've also seen some data, and we're going to encode that in the likelihood by saying, well, we're going to encode the probability for the data given a value of mu. These are two sources of information, and you want to basically fuse them, and you do that through Bayes rule. And if you do that, you'll see that this here, or this guy, is the likelihood, and these are all the factors in the beta distribution that have mu inside them. The beta distribution also has a normalization term, but it's not a function of mu. And since we are working here on a probability distribution over mu, we kind of drop that out, and because we can always normalize later by summing over or integrating out the numerator. So this is going to be a probability distribution, this posterior, that's proportional to mu to the power n plus alpha minus 1 times 1 minus mu capital N minus n plus beta minus 1. This again looks like a beta distribution. You know it's going to be normalized. So in front of it there will be there will be these gamma functions, but we don't care about them. We can already see that because we know this is a normalized function, this has to be a beta distribution. But now with a new alpha, n plus alpha, and a new beta, capital N minus n plus beta. So this is the posterior, this is the knowledge about the parameter mu given the data and given the fact that we assume a beta distribution to represent our knowledge about this coin. With that, we can basically go to the next stage, which will be model evaluation. I could choose another model, for instance, another beta model with different values for alpha and beta, and I could compute the relative probabilities of these two assumptions. We'll skip that for now. We'll do that in the probabilistic programming class that will follow this class. And let's say that we accept this model, and so we have now a distribution over mu that contains everything we know about mu, all prior information encoded in the prior, plus all information that's encoded in the data through the likelihood function, and by multiplication or Bayes rule, we have fused that information into a posterior. So now we're going to go to the prediction. We want to predict the probability that the next observation is going to be had, given the data and given that basically my model assumptions. So this, and I'm just copying here what we did in the previous video. I extend the conversation to include my parameters. So going from, let's say, the right-hand side to the left-hand side is basically marginalization, right? We extend the conversation. We include, we say, well, the probability for that I throw head given the data is the probability that I throw head given my parameter. I mean, I have a model for this, namely this is the Bernoulli distribution, times the probability of, well, basically, what do I know about this this parameter, the posterior for the parameter, and then I basically sum over, I integrate the parameter away, because I don't really care about the parameter, I only care about the probability that I throw head given the data. So this, we can fill in here the Bernoulli distribution, we fill in this posterior, which was the beta, and this formula, and you just have to look that up or find on the internet how to compute that, but this has an analytical solution, and the analytical solution is given here, n plus alpha, so the number of throws of heads plus alpha divided by the total number of throws plus alpha plus beta. This is actually a very famous rule because throwing a coin is sort of an example that fits on very many problems. So it's called Laplace's rule of succession. And that's it. We can encode that up. So there's a piece of code here in the lecture notes. And so here what we did is we chose two different priors. One, a beta distribution alpha equals 5 and beta equals 5. And the other is the uniform prior, b equals 1 or alpha equals 1 and beta equals 1. And after 3 throws and 2 times heads, basically this is the posterior over mu for this prior, and this guy, the solid line, is the posterior for this prior. So in this case, when I've seen just very little data, we see we have quite different beliefs for what mu is. The prior is very important because I've seen very little data. As I start to make more observations, here I have 10 throws, here I have 50 throws, and here I have 150 throws. And now after 150 throws, and of which we observe 61 heads, you see that both distributions have basically are peaking around 0.4. The real mu that we threw with was 0.4. So we don't have, I make two observations here. One is that the prior is much less important if you observe more data. Basically, we started out with different assumptions about the coin, but we got so much information from the data because we got so many throws that the likelihood term kind of overwhelmed the prior term. The second part is no matter how many coins, how many tosses we do, we'll never get a real spike on 0.4. There will always be some remaining uncertainty. It could be that this is a fair coin, and just by accident we happen to observe 61 heads and 150 in 150 throws, right? So there is a non-zero probability that the mu is 0.5 and a non-zero probability that mu is 0.8 and so forth. So that's why you will always see it will become more and more picky, but it will never go to zero for basically for the full range 0 to 1 if you observe at least one head and at least one tail. Most importantly, with more data, the relevance of the prior diminishes. Or in other words, if you have very little data, then the information that you know about your coin is mostly determined by the prior. So this is the most important thing about Bayesian machine learning. We have, in the first part, we sketched the general framework. And in the second part, we instantiated this for a particular application. You make your choices for your prior and your likelihood. From there on, it's all just computation. We happen to choose a prior and a likelihood that if I multiply them, I actually get an analytical result. And that analytical result is again a beta distribution. So that's of this property that when you choose a prior such that after multiplication with your likelihood you get a distribution that is again of the same form as your prior, but now of course with updated parameters. We call these two distributions a conjugate prior. So the binomial and the beta distribution are conjugate of each other. So beta is a conjugate prior for the binomial distribution, and it's a very good choice because you don't have to go to numerical recipes. You basically get analytical solutions. We also got an analytical solution for prediction, and so everything is fine in this example. We don't need to go to any numerics. Okay, so that's the essence of Bayesian machine learning, and no matter how complex the problem gets, it's going to be this recipe. You make assumptions for your prior, and you make an assumption for your likelihood. You do machine learning. Basically, you update your parameters, and then you can do model evaluation, if you will. And then you apply it in your to your application, and that's it. So I'll see you in the next class.